Let's look at a hypothesis test for correlation. Darren Ireland, a graduate student at Montana State University, wanted to weigh Weddell seals in Antarctica to see whether the population was thriving or not. One way to do this is to take overhead photographs to estimate the mass of the seal. But how do we know that the photographs can be used to accurately estimate the mass of the seal? First, we take the photo. Here he is, photographing a Weddell seal. Then we weigh the seal. This is a livestock scale, big scale. Later, we measure the overhead width from the photo. Then we plot the data on a scatter plot. In other words, mass and overhead width. This is what the overhead width looks like, OW. We suspect that there is a positive correlation between overhead width and mass. Here are the overhead widths in centimeters of the adult female seals measured from photographs, and the masses in kilograms of the seals. Find null and alternative hypotheses. Null hypothesis, no connection, no correlation. It always has an equal sign. It's of the form rho equals 0. That's the Greek letter rho. I know it looks like a P, but it's a rho. Trust me. The alternative hypothesis is that there is a connection, there is a correlation, and that's going to be of the form rho does not equal 0, rho is less than 0, rho is greater than 0. Okay, the null hypothesis is that there's no correlation between overhead width and mass of a Weddell seal. We can state it symbolically, let rho equal the correlation between overhead width and mass of a Weddell seal. The null hypothesis is that rho equals 0. The alternative hypothesis is that rho is greater than 0. We choose this as the alternative hypothesis because we want to test the hypothesis that there is a positive correlation. Remember earlier we were told that we suspect that there's a positive correlation. Okay, so here are null and alternative hypotheses. We want to do a hypothesis test on the correlation between two quantitative variables. Do the data satisfy the required conditions? Linearity. Okay, first, the scatter plot has to look straight. So you want a scatter plot that doesn't have to be exactly straight, but has to look something like that. Equivalently, the residuals don't follow a curve. You don't want residuals that look like this, or like that, or, like this. You don't want stuff like that. Independence of residuals, no pattern, no trend, no clumping. Equal variance, homoskedasticity, the longest word we've seen this semester. That means the variance of y is about the same at every value of x. So again, you don't want the residuals, you don't want the pattern of residuals to look like this, where, okay, you've got the fan pattern. The variance is pretty small for small values of x, and the variance of y increases for large values of x. You don't want something like that. And you want nearly normal residuals. A histogram of the residuals should show that their distribution is nearly normal. Okay, this is the actual plot of the residuals from this study. He didn't have just 7 data points. He had a lot more than that. Notice linearity. The scatter plot looks straight. Well, the residuals don't follow a curve, so this looks pretty good. Independence of residuals. We don't see any patterns, trends, or clumping. Equal variance. The variance of y is about the same at every value of x. Again, we don't see that fan pattern that we talked about. And the residuals are nearly normal. Notice they're clustered around this midline. They thin out as we head away from the midline. That's good. Okay, so those are our null and alternative hypotheses. There are several ways to test a hypothesis about correlation. Here's one way. Calculate the sample correlation coefficient R. Use it to determine whether we should reject or fail to reject the null hypothesis. So again, here are the data we're working with. That's the overhead width and the mass of these seals. Using a graphing calculator, or SPSS or Excel, we find that the sample correlation coefficient R between these two data sets is 0.772. Now, sometimes software will present correlations in the form of a table. The correlation between width and width is 1, and the correlation between mass and mass is 1. That's obvious because you can, if you know the mass, you know the mass. The correlation between mass and overhead width is 0.772, and vice versa. Do we reject or fail to reject H0, the null hypothesis? Here's our table. In this case, rho is greater than 0 is our alternative hypothesis, so we would reject if R is greater than R star. So let's find the critical value R star. Our book doesn't have it, but you can just enter correlation table critical values into a search engine. And here's what we end up with. Okay, the column we want is the one-tail probability, 0.05. So this is one-tail test, 0.05. That's what we want. And the row is DF, in other words, degrees of freedom, n minus 2. With tests of correlation, the degrees of freedom is the number of data points minus 2, or number of pairs minus 2. So it's 7 minus 2, which is 5. So we want this row. Okay, so we want this row, we want this column. So 0.669, that's our value of r star. Okay, and this would be, this is what the chart would look like if n is greater than, if the degrees of freedom is between 21 and 100. Okay, since our alternative hypothesis is rho is greater than 0, we reject the null hypothesis if r is greater than r star equals 0.669. Our sample correlation coefficient r is 0.772, which is greater than r star equals 0.669. So we conclude that the null hypothesis is false. We reject the null hypothesis. Here's another way to test the hypothesis, test a hypothesis about correlation. Calculate t equals r times the square root of n minus 2 over 1 minus r squared. Use the t distribution chart to determine whether we should reject or fail to reject the null hypothesis. Also find the p-value. Okay, so here's the formula. We plug in r equals 0.772, n in this case is 7, and we end up with t equals 2.716. Now, again, we use the, here's what the chart would look like. If this is the alternative hypothesis, this is what our rejection region is going to look like if we're working with t's equivalently. To find the value of t star, look at the t distribution table in our textbook, or enter t distribution table into a search engine. Here's what we end up with. Again, we want the one-tail probability to be 0.05, and we want the rho to be degrees of freedom, n minus 2, that's 7 minus 2, that's 5. So this is what we're working with. Okay, so it looks like 2.015. That's going to be our value of t star. Since our alternative hypothesis is two-sided and of the form rho is greater than 0, we reject the null hypothesis if t is greater than t star. We saw that t star is 2.015. Thus, we reject the null hypothesis if t is greater than 2.015. Ho-ho, we have t equals 2.716, which is greater than 2.015. So we reject the null hypothesis. Let's find the p-value. You remember how to find the p-value if you're working with t. In this case, rho is greater than 0. That means the area to the right of t is going to be the p-value. We want to find the area to the right of t equals 2.716. On the TI, go to Dister and choose T CDF. Here's what a t distribution looks like. Looks a little like a normal distribution, a little fatter in the tails. We want to know the area to the right of 2.716. So in this case, A, our left endpoint is 2.716. That's why that's here. B, our right endpoint is going to be infinity. There's no infinity button on the calculator, so we may as well just choose 10, because 10 is way out there. And the degrees of freedom is 5. We get 0.0209. That's the p-value. Another way to test a hypothesis about correlation is to use the hypothesis testing feature in the graphing calculator. Using the graphing calculator, determine whether we should reject or fail to reject the null hypothesis. Okay, so quickly I'll say this and then I'll show you. Press Stat, Tests, Linear Regression T-Test. Your data are in L1 and L2. That's assuming your data are in those lists. Frequency is 1 because, each of those data points appears once. You would choose beta and rho is greater than 0 because rho is greater than 0 is our alternative hypothesis. By the way, beta is the slope of the population regression line y equals alpha plus beta x. If rho is 0, that would imply beta would be 0 as well. So that's why we say beta and rho are both greater than 0. Regression equation y1, or you can just leave it blank. Y1 would put the equation of the regression line as y1 on the graphing screen. That's pretty cool. And then you choose calculate. So let me show you how we do that. Okay, turn the graphing calculator on. We've already put in the data, so we quit. And then we go to Stat, Tests. We want, let's see, we want, linear regression t-test. That's what we want. Okay, x list is L1, y list is L2. Everything's fine except we want beta and rho to be greater than 0. That's what we want. Regression equation, this is how we get y1. We press bars, y bars, function, y1. So we get the y1 there. And then we do calculate. Okay, and that's what we end up with. The p-value is 0.0210. Check this out. That's more or less the p-value that we obtained earlier, so we reject the null hypothesis. Again, p-value 0.0210. Note that it also tells us t equals 2.714. That's what we calculated earlier. It also tells us the least squares regression line y equals a plus bx, which best fits these data, is y equals a in this case is negative 45.4077, plus b, that's 5.74659x. Again, those are the values a and b. Those are the coefficients for the regression line. And it also tells us that r is 0.7718. We already knew that, though. How can we improve the model? Well, you can include more variables. The best model the researcher developed was mass equals negative 134.1 plus 3.635 times overhead width plus 0.040 times side area minus 2.497 side height. This is an example of multiple regression. We estimate mass based not on just one variable, overhead width, but more than one variable, overhead width, side area, side height. And this is a Weddell seal pup. They're pretty helpless creatures when they're born. They can't really get around that well.
Yeah.